Yes, I'm picking up where I left off, talking about the geometry of second-order systems. We were looking at this figure down here. Actually, I fixed this also for case 3 while I was taking a little break there. So this figure is very important, as we shall see when we study what's called the root locus. And I have my 4 cases that I want to discuss or show. The first case was the overdamped case where we have 2 real roots. Now, what I've shown here is the case where our omega n is on this circle here, which we'll see in a minute that has to be the case. So zeta, if zeta is 1 and omega n, well, omega n is omega n, then zeta omega n will be out here at this place where the circle crosses the real axis. So this would be the real part of our root, or not the, well, both parts are real, but if we go back and look at the equation, there was a common part. This is for case 1. The common part is zeta, negative zeta omega n. And then that's case 2, but actually if we go back up here, yeah, here's our root, our expression for our root in general. If zeta is, well, if zeta is greater than 1, then we have 2 roots. One that they're centered around this point. One will be to the right of it, and one will be to the left of it. So we go to this point, and then we go plus and minus this amount to the left and to the right, depending upon which root we're talking about. So if we look at our picture again, that would be the case here. This is actually the case of zeta equal 1. We'll see that in a minute. But zeta omega n is out here, and then the zeta omega n minus that other part of the root would be here, and zeta omega n plus the other part of that root would be here. So we have 2 real roots that are distinct from each other. Now case 2 was the underdamped case. Okay, and this is the case where we have 2 complex, well, a complex conjugate pair. So zeta is between 0 and 1, and that's this orange root here, and then there's another one down here. These are they have the same real part, which is negative. Okay, let's scroll back up and look at that, case 2. So they have the same real part, but then the imaginary part, well, it's here, is up and down parallel to the imaginary axis by a distance omega n times the square root of 1 minus zeta squared. And we actually call that omega d. This is the damped natural frequency, and it's the frequency at which the system will oscillate. So if we look at our picture again, that's this case here. So we have a negative real part that's common to the 2 roots, but then the imaginary part of each root is the same, but one is positive and one is negative, and it's up by omega d and it's down by omega d. Now normally we don't show the bottom half of this picture. This is a picture of the complex plane, because what's happening down below the real axis is exactly the same as what's happening above the real axis. So there's no reason to duplicate that. I've simply shown this root down here because it's the first time that we've done it, and you should be aware that there's not just one root, there's another one hiding down here that we normally don't show. Okay, now case 3 was the case of zeta equal 1, and so S is equal to minus omega n, and that is shown with these kind of turquoise roots here. And I've shown them, these are really on top of each other, but I've shown them sort of staggered so that you can see that they're real, but there's 2 of them there. They're repeated. So we have no oscillation there, but we call this the critically damped case. We'll see, this is a borderline case, and we'll see that very distinctly when we study the root locus. Okay, now the last case, which was case 4, was the undamped case. And in the undamped case, zeta is 0, and therefore we have two roots, one up above the origin along the imaginary axis. There's no real part, or the real part is 0, and one below. And those are shown also on this diagram. This is the yellow. So there's a root up here, and there's its conjugate pair down here below. Okay. Now there's a lot of things that can be seen from this, and I'd like to make some comments on that. If we look at, say, case 2, the underdamped case, the distance out of that root from the origin, we can see that its coordinates are negative zeta omega n, and then plus or minus omega n times 1 minus times the square root of 1 minus zeta squared. So if we use the Pythagorean Theorem to figure the distance of that root out from the origin, we put the real part in here, we put the imaginary part in here, we square both of them and add them. Well, we can do a little bit of manipulation. We have an omega n squared in both terms, so we just simply take the square root of that and put it on the outside of the square root curve. Oh, look what happens then. We have a zeta squared term and a minus zeta squared term, so they kill each other off, and we have a square root of 1, which goes away, and so the distance out of these roots anywhere along this curve is going to be omega n. So the curve actually represents a locus of constant omega n. So any system or systems that have poles on this curve are all going to have the same omega n. Now they don't oscillate at the same frequency, because remember the oscillation frequency is actually omega d, and this is omega d up here on the top. So if you increase your damping, then what will happen is you actually move down this curve this way. And if you'll notice, if it had a root out here, for instance, that's going to be at a lower distance up than the root that I've shown. So this is greater damping this way, and this system would oscillate at a lower frequency, so it'll have a slower oscillation than a system whose roots are in the position that the orange roots are shown. So any horizontal line is a line of constant omega d. Now, the other thing that's interesting about this too, there's a lot of things to be seen in this, is remember that the percent overshoot is related only to zeta. It is not related to omega n. Since that's the case, well, I haven't said this yet, so let me back up a little bit and cover this real quick. If we look at, well, let's see, have I done this yet? Oh, yes, I've done this below here. But if we look at the cosine of this angle right here, it's going to be the adjacent side, zeta omega n, divided by the hypotenuse, which is omega n. So the cosine of this angle is equal to zeta. And what that means is that since any point, any roots along here would have the same theta angle here, and the cosine of theta is equal to zeta, then all of these roots along this line here, shown as example, are the same zeta. And since they're the same zeta, that means they have the same overshoot. So this is a line of constant percent overshoot. This is a line of constant damped natural frequency. This is a line here. Now this determines, zeta times omega n actually determines how fast the oscillations die off. So anything along this line will have the same rate of decay of oscillations regardless of where the roots are along here. So there's a lot of information contained in this figure, and actually that's the confusing thing about it, in that it's just too much information there, or it takes some time to understand it. But oftentimes what you do is you look at this figure and you look at the response of a system, and you correlate what this figure is telling you with what you see in the actual dynamic response. And if you see a discrepancy, then there's a mistake somewhere, or you're not understanding something right. And so you have to clear that up. But this figure is a very useful tool for looking at the how the second order step response of a system, and comparing two or more systems. Okay, I'm out of time, so I'll stop here, and I hope that was helpful to you. One thing that I do say here at the end is that this figure actually leads very, very nicely into the root locus of systems, and the root locus will be covered in some later videos.